So let's first just revisit finding global extrema, because I think that's something it's kind of separate from all the other graphing stuff. Like, it's not something you really do when you're graphing, is finding the absolute max and absolute min. You can, but it's not super necessary. So let's talk about global / absolute extrema for a moment here. So finding the global extrema is typically, I think, it was a 2 or 3 step process. Step 1, you're going to find the critical values. And the way you do that is by setting the derivative of your function equal to 0, and also / finding where it's undefined. And don't worry, we're going to walk through an example in just a second here. The second thing is to then evaluate your function, not the derivative, the actual function, f of x, at each critical value and any endpoints. Because typically, when you're deciding if you have an absolute maximum or an absolute minimum, it's usually on a closed interval. It technically doesn't have to be, but the extreme value theorem does necessitate that. And then finally, the last part, which is just the biggest one is the max, the smallest one is the min. So the largest function value is the absolute or global maximum. And likewise, the smallest function value is the absolute minimum. That's our process, and it's always the same. So let's look at an easy example here. I mean, easy is relative. Let's look at an example. I know math teachers tend to get in the habit of saying things are easy because for them it's easy because they've done it for 20 plus years. So sometimes they say something is easy and I know it's not really, and I try not to, but it's hard not to sometimes because it's like, oh yeah, this should not be a terrible example. But let's look at a hopefully not too terrible example. Let's look at, say, f of x equal to x times x minus 5 squared on the interval from, oh, where was that? I lost my spot. Fine. Let's say from 1 to 6. Okay, I kind of zoomed in a little bit too much. All right, step 1. Got to find the critical values. We're going to take our derivative, set it equal to 0. You have a couple choices here. You could multiply out the function before differentiating or not. I'd probably rather not. So let's just take the derivative. Sorry, f prime of x is going to be, I need to use the product rule here. Derivative of x is 1 times the other piece left alone, plus now it's x times the other piece left, the derivative is going to be the derivative of some stuff squared is 2 times our stuff. Technically, we should finish this off with the chain. So it should be 2 times our stuff to the first power times the derivative of our stuff, but that's also a 1, so I'm not going to write any of that, but it's there, right? We're still thinking chain rule because our insides are more complicated than just x. And we're set that equal to 0. Now, this problem, it can be a little bit challenging. I think we could maybe all probably easily see that x equal to 5 is for sure a critical value. If you plug in 5 here, you get 0, and if you plug in 5 here, you get 0, and 0 plus 0 is 0. There is another critical value here, which is harder to see. So when you have something like this, where you've used the product rule, you often have to do some factoring to be able to really find all the critical points or values. So from this part and this part, I'm going to factor out an x minus 5. From here, I'm left with an x minus 5 to the first. Come on in. Talking about global extrema. And from here, I factored out the only x minus 5 that was there, so I'm left with the 2x. Now, if we simplify the inside of this here, we've got x minus 5 times x plus 2x is 3x minus 5. Setting each part equal to 0, x minus 5 equal to 0 gives us x equal to 5. That's one of our critical values. and 3x minus 5 equal to 0 gives 3x equal to 5, or x equal to 5/3. And I wish I would have done, not really wish. So I just want to point out, if I had given a different interval, right? If the interval had been, say, from like 3 to 6, we wouldn't check this critical point here because it's not inside the interval, or wouldn't have been inside the interval. It will be here, right? 5/3 is definitely bigger than 1, but it's important to check, right? I guess I could have listed that in my steps. When you're finding absolute extrema on a closed interval, the points you're checking all have to be in the interval that we're looking at. So now, step 2, evaluate. We're going to evaluate, bless you. I mean, I wasn't, whatever. You can say bless you for a cough. It's fine. Okay, it was like, it felt like kind of a cough sneeze. Anyway, bless you regardless. Gesundheit, whatever you want to say on that. So we're going to look at f of 1, f of 6, f of 5, and f of 5/3, which is going to be the worst part. I do recommend when you're doing this that if you haven't already factored the original function, to factor the original function. Like if you're having to do it by hand, it's much easier to plug this into a factored versus non-factored thing. So f of 1 is going to be 1 times -4 squared, which is going to be 16. F of 6 is going to be 6 times 1 squared, which is 6. F of 5 is going to be 5 times 0 squared, which is 0. F of 5/3 is going to, oops, yeah, no, that's right. F of 5/3 is going to be 5/3 times 5/3 minus 5 squared. Okay, fine. We have to do the work here. It'll be 5/3 times 5/3 minus 5 is 5/3 minus 15/3. That's 5/3 times 5 minus 15 is -10. Still over 3 squared. -10/3 squared is 100 over 9. So we end up with 500 over 27. Ugh. All right. Which of these is obviously the smallest? 16/6, 0, or 500 over 27? 0, right? You don't have to whisper. You can say it loud. Say it loud. Everybody say it. Thank you so much. So I would say that, and again, there's a lot of ways to phrase your answer here. The most kind of inclusive way is to say the point 5, 0 is our absolute minimum. Again, other ways to phrase this is we have an absolute minimum at x equal to 5. We have an absolute minimum value of y equal to 0. So the place that it occurs at is the x coordinate. The value is the y coordinate. All right, which one's the maximum? Well, it's definitely not 6, but is it 16 or is it 527ths? I don't know. I guess to figure it out, we'd have to multiply 16 by 27 over 27. It's okay, fine. What's 16 times 27? Who knows? 16 over 1 times 27 over 27 is 6. Sure, fine. We can do 16 times 27 a long way. 2, 4, 6 times 2 is 12 plus 4 is 16. And then I think the 500 is going to, that'll be bigger, but we end up getting 432 over 27. So this is the bigger one. Cool. So we have an absolute maximum at the point 5/3, 527ths is our absolute max. Cool. Questions about this example? I can grab another. That looks terrible. Oh yeah, we should do one of those. Oh, I have all these other ones. A lot of examples. All right, let's do another example here. I think there's one here. Really, yes. Yeah, you're good. It's only gonna be a little bit gnarlier, and then we'll move on to the more of the graphing stuff. So let's look at this example. G of x equal to, yeah, we should do this one. 6x to the 5/3 minus 15x to the 2/3 on the interval from -1 to 8. We'll go to 8. It seems dicey. Is this, so I should point out, I should write more words. Find the absolute extrema of this function on that interval. So I should actually ask you all, or point out, does this function actually meet the criteria of the extreme value theorem? It should if someone's asking you this question. If someone says find the extreme values on this interval that's closed, they should have given you a function that you can do that for. So we're certainly on a closed interval. Is this function continuous on that interval? It is, right? How do we know? Well, that's a good question. These odd roots are kind of our saving grace here, right? You can always take an odd root of a positive or a negative number, right? You can definitely take the cube root of -1 or the cube root of -8. And so then having a cube root and then to the 5th power or a cube root in the 2nd power, we're safe here. So we're good to go. All right, critical values. Whew. G prime is going to be the derivative of 6x to the 5/3 is 6 times 5/3 x to the 2/3 minus 15 times 2/3 x to the -1/3. That looks kind of gross. We're going to see where this is 0 or undefined because there is a place where this is undefined. There's actually, no, there's one place, yeah. So let's simplify a little bit. 6 times 5/3 is 30/3, which is 10. This is 10x to the 2/3. 15 times 2/3 is also 10. I should, okay, fine. So this is, again, a lot of these problems, when you're trying to find critical values, it's absolutely, no pun intended, necessary that you have to factor. There's no other good way of solving things like this. So you really, this is where, like, we didn't do a bunch of simplifying before with all the derivatives. Now you actually really have to be able to simplify these derivatives so you can find where you have critical values. So I'm going to factor out a 10, and I'm always factoring out the lesser power of the thing. So I've got x to the 2/3 and x to the -1/3. -1/3 is definitely smaller because it's a negative number. So I'm going to factor out an x to the -1/3. And now let's see what I'm left with. Ooh, x to the what? Good question. X to the what right there? Well, here's what I'm really doing. If I divide out an x to the -1/3, I'm literally actually dividing x to the 2/3 by x to the -1/3. And when you divide powers like that, what do you do with the powers? Yeah. And 2/3 minus -1/3 is 2/3 plus 1/3, which is 3/3, which is 1. So we really have an x to the first minus 1, right? We factored out the entire 10x to the -1/3. When I do this, it always feels a little bit wrong. So I always like to check. If I multiply this all back through, 10x to the -1/3 times x will give me a 10x to the 2/3. And 10x to the -1/3 times 1 will give me a 10x to the -1/3. So it feels right. But I do like to do that check. If I multiply it back through, do I actually get back to where I started? And I do, if I've done it correctly. All right. I want to point out, if you were just asking where this is equal to 0, the only solution would be x equal to +1. If you're trying to figure out where this is undefined, then x equal to 0 would be a place where this is undefined. It feels like it just got like extra cold in here. Like, is it just like, is the air blowing on? I don't know. It feels like all of a sudden, like, anyway, I don't know. Sorry, it doesn't really matter. But just to kind of clarify here, if I'm going to rewrite this one more time, I'm going to write this as 10 times x minus 1 over x to the +1/3. It doesn't matter. I don't want to say that. It matters. It kind of doesn't matter a whole lot in that whether you know that this is making it 0 or undefined, it's still a critical value either way. But it is good to know what it actually is. So x equals 0 makes this function, this derivative, undefined. X equals 1 makes this derivative equal to 0. They're both critical points, though. All right, let's go ahead and find out. That was our first step here. So now we're going to plug them all in. And once again, Both of these critical values are in the interval, so we have to check them both. I should have made a different interval, but I didn't know what the critical values were going to be ahead of time, so I didn't know. So we're going to check f of 0, f of 1, and then f of -1 and f of 8. And I know I said the thing before, I think it's still true. It's probably going to be in our interest when we're plugging these things in. Most of them are fine. Let's back that up, James. The last one we might want to do something for, but if I plug in 0, I'm going to get 0. Right? 0 to any positive power is 0. 0 minus 0, 0. F of 1, 1 to any power is 1. So I'm going to get 6 times 1 minus 15 times 1, which is -9. F of -1, I have to be a little bit more careful here. I'm going to get 6 times -1 to the 5/3 minus 15 times -1 to the 2/3. All right. One of those -1s to a power ends up being -1. One of them ends up being +1. Here's why. What's the cube root of -1? Is it +1 or is it -1? It's -1. So both of these, when you do the cube root part, you get -1. But then -1 to the 5th is still -1. -1 squared is +1. So -1 to the 5/3 is -1 cube root, and then to the 5th, that's -1 to the 5th, which is -1. But -1 to the 2/3 is the cube root of -1, but then it's squared, so it's -1 squared, which is +1. That's what's happening there. So we end up getting 6 times -1 minus 15 times +1, which is -6 minus 15, which is -21. And finally, the one not dreading, but it's going to be a little bit gross. 6 times 8 to the 5/3 power minus 15 times 8 to the 2/3 power. This is where I probably would have factored ahead of time if it wasn't the only one I had to do it for. 8 to the 2/3. Well, just like when we did -1 to the 2/3, we did -1 to the 1/3 and then squared it. 8 to the 2/3 is really 8 to the 1/3 squared, which is 2 squared, which is 4. And 8 to the 5/3 is really 8 to the 1/3 to the 5th, which is 2 to the 5th, which is 32. So we end up getting 6 times 32 minus 15 times 4, which is, okay, it's not the best ever. 180, 192 minus 60 is 132. And then if this was a test and I had limited time, or if I was just being lazy, I would do this. I would circle this and be like, there's your minimum. I would circle this and be like, there's your maximum. That's the fastest way to write the answer to that. It's the way I'm writing it now because I don't want to take another page paper, honestly. But like that's what I would really do if I was taking a test. But yeah, min, max, move on to the next question. The only thing about this, what I've done now is okay. Nope. That's not what I wanted to do. This one, oh, cool. Yeah, it went away. What's this magic? Okay, so global extrema, this is always the process. So be careful when if someone's asking for absolute versus relative extrema. Absolute's always this thing where you take your critical values and typically your endpoints and plug them back into the original function. Whereas relative extrema or local extrema, very different process. And honestly, I think we should just start talking about the relative extrema and the concavity in the context of graphing, because that is really what you're going to do with it. So let's look at some examples. Let's say, for example, let's graph f of x equal to x squared times x plus 4. Now, when someone says let's graph or graph a thing, there's usually some things that they expect you to do. And here are my list of typical teacher expectations for when someone says graph it. So specifically graphing, they're going to expect you to find the x and y-intercepts, any asymptotes, so vertical asymptotes and horizontal asymptotes. What I typically refer to as the first derivative stuff, meaning find any critical points in relative extrema. I should just say relative extrema. And then the second derivative stuff, which is the concavity and the inflection points. I know we haven't talked about that yet. We're about to talk about it. I should say relative extrema and the increasing, decreasing. Those are, to me, that's a pretty exhaustive list. There's a couple other things you could throw in there. Like occasionally a function might have a slant asymptote, or occasionally you might have some symmetry, like your graph might be even or odd. But typically I would say this is my usual list of things I'm going to look for. So right off the bat, looking at this function, I can see that that's a polynomial, right? If you multiplied it out, it said it was x cubed plus 4x squared. All my powers of x are nice, non-negative integer powers. Polynomial means it's continuous everywhere, means it's differentiable everywhere, means you don't have any asymptotes, period, none. No vertical, no horizontal. Great. So let's find the intercepts. How do we find the y-intercept? I know it's been a while. We set, right, always the other one equal to 0. Set x equal to 0, you're going to get y equal to 0 times 4, which is 0. Ooh, yeah, here's another good piece of advice, I think. When you find the y things, meaning the y-intercept or the y-coordinate of your critical point or the horizontal asymptote, when you find the y things, it's usually easier to look at the multiplied out form. Not always, but most of the time. When you're finding the x things, like your x-intercepts and your vertical asymptotes, it's usually easier to look at the factored form. It's just something I've noticed over the years, but we'll talk about why. So to find the x-intercepts, we're going to set y equal to 0. So setting y equal to 0, we're going to get 0 equal to, it's definitely better to look at the factored form here. X squared times x plus 4. It's more obvious, in my opinion, that we're going to get x equal to 0 as a intercept and x equal to -4 as an intercept by looking at the factored form versus the multiplied out form. All right, but that's the easy stuff. There's no asymptotes here again, right? All polynomials never have asymptotes, always true. So let's skip on to the relative extrema, aka the first derivative stuff. So the first derivative stuff. Probably the most useful thing you get out of the first derivative stuff is the sign chart for the first derivative. So I'm going to take my first derivative, which I probably didn't do a good job of picking this function because it's going to be not very nice. Oh, well, not every function has nice values. So our first derivative is going to be, let's see here. Let me ask you all. Do you want to use the product rule or not? I think not, right? I mean, you can, but it's easier. If it's easier to multiply something out or simplify it before taking the derivative, usually not a bad idea. So we're going to get 3x squared plus, ooh, James, good choice, 8x. Okay, it's not that bad. Factor out an x. We've got a 3x plus 8 equal to 0. So we're going to get x equal to 0 as a critical point. And if you solve this, 3x equals -8, x equals -8/3. We put those on the number line. Those and only those. So if 0 isn't a critical point, you should not put it on your number line. So I'm going to put 0 and -8/3 and my derivative over here. And then we just want to test in each of the intervals whether the derivative is positive or negative. So over here, if I pick a number bigger than 1, like 5, positive, positive, the whole thing's positive. And then you can either keep picking points, or you can do the thing where you say 0 came from there, odd power, which means the sign is going to change. -8/3 came from there, which has an odd power, so the sign is going to change. which means our function in this interval is increasing, in this interval is decreasing, in this interval is increasing. And this right there, the stuff I just drew in red, is probably the most useful thing we've got. It's going to show you the shape of the function. It's going to do this, and then that, and then this. I know it's harder to see at home, but we should write down that we have a relative. Okay, at 0, do we have a relative maximum or relative minimum? Right there. Is this a bottom or a top? The bottom, right? You're bottoming out there. You're going down, 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 and then up, 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 up. So we have a relative minimum at x equals 0. And we already know what the y value is. If x is 0, y is also 0. On the other hand, we have a relative maximum right over here because we're increasing to the left and decreasing to the right. So it's going to be relative maximum at -8/3, comma. Here's what I do if I don't want to spend the time to find the point right now. I write f of -8/3. I was hoping to save this room for the graph, but we should find the second derivative stuff. So, typically, yeah, fine. We can find that. It's not so terrible. -8/3, comma. If I plug in -8/3 to the original function, because that's the y value that we're going to graph here, it's going to be. I don't love it. Sorry, I'm trying to find a good place to put this here. F of -8/3 is -8/3 squared times -8/3 plus 4, which is 12/3. Yikes, that's gross, James. Good choice. So that's 64/9, and then -8 plus 12 is 4/3. Yeesh, yeesh. 256/27. That's kind of terrible. Okay, I'm sorry. It's pretty terrible. I'll point out this is gross, but you can get a decent idea of what that is. That's not too far from 10. Right? That's almost 270/27. So it's somewhere between like 9 and 10. Yeah, so it's a good point to pick better numbers. Let's look at the second derivative stuff. So to find the second derivative stuff, we're going to take the second derivative and set it equal to 0. So our second derivative is going to be 6x plus 8. We set that equal to 0. We're going to get 6x equal to -8, x equal to -4/3, or -8/6. And that's our only critical point for the second derivative. So over here is f double prime. Put our one critical value there. And then decide or determine what the sign is of the second derivative. So if x is bigger than -4/3, like 0, our second derivative at 0 is just going to be 8, which is positive. On the other hand, if x is less than -4/3, like -3, 6 times -3 is -18 plus 8 is a negative number. What does that mean? And again, we'll talk a little bit more about the second derivative in just a second here, because I know we haven't really talked about it a lot. But what it means graphically, there's a lot of ways of saying this. One way to say it is that the function opens downwards when it has a negative second derivative, and upwards when it has a positive second derivative. Or it's concave down, concave up. But I will point out, your concave up or your concave down, this might not look parabola-like. It will for this example, but there are lots of other functions. Like, for example, this is a quick example. Sorry. F of x equal to 1/x. Right? This function here is concave up in this interval here because it's still opening upwards. And over here, it's concave down because it's opening downwards. Another way people describe this, which I actually really come to enjoy, okay, is that if the function is concave up, the tangent line should be below the function. If the function is concave down, the tangent line should be above the function. We'll talk more about it. Don't worry, but it's kind of a nice way of seeing it, I think. All right. So last thing we're going to write down before we graph it is we also have an inflection point. So an inflection point, and we're going to say this all again. Don't worry. An inflection point is where the concavity changes. It doesn't matter which way it changes. So unlike with relative extrema, we're going from left to right. We're always going left to right, always left to right, always left to right. If you go from positive to negative, you have a relative maximum. If you go from negative to positive, you have a relative minimum. For second derivative stuff, it doesn't matter. If you go negative positive or positive negative, if the concavity changes, we have what's called an inflection point. So we have an inflection point at -4/3, comma, f of -4/3. Which I'm not, fine, sure. It's gonna be -4/3, comma, 16/9 times 8/3 is gross. Also, it's 128/27. It's not important, but it feels slightly important to me that I have to graph it. All right, then we put it all together. Your graph does not have to look perfect. You just need to get the important points on there. So I'm going to start with the intercepts. I have an x-intercept at 0, I have a y-intercept at 0, and I had an x-intercept at -4. No asymptotes. I had a relative minimum at 0, 0. So I know it's going to be a minimum right there. And I had a relative maximum at -8/3, comma, some y value. I don't actually care about getting even remotely close to right. -8/3 is between -2 and -3. It's like right about there. So I'm just going to kind of eyeball it and say right about there. So there's my relative maximum. And then really, I don't even look at the second derivative when I graph it most of the time. I know that my function should be increasing and then decreasing and then increasing. I think it's nice at your relative extrema to kind of round it out like that so that you can, before you actually graph the thing, so that you don't like come at it too sharply and then have to like turn around and make it look gross. So here we go. Whoops, no, that's fine. That's okay, James. Here is our function. F of x equal to x squared times x plus 4, or x cubed plus 4x squared. We have our relative maximum at -8/3, comma, whatever that gross number was, 256/27. We have a relative minimum at 0, 0. We have an x-intercept at -4, 0. And we have our inflection point at right about there. -4/3, comma, 128/27. Okay. But look at the inflection point there. The inflection point is literally where you go from being opening downwards to opening upwards. Another way to talk about the inflection point, and I kind of like this, is imagine you're a car, and so imagine this is like a road on a map. You're looking down, this is your road map, here's the road, it's kind of curvy and fun to drive on, and you're driving a car, and currently in my car, I'm turning to the right. Right? I'm turning right, I'm turning right. I'm really turning right, making a hard right turn there. Still kind of vaguely turning right, just a little bit. But then at the inflection point, I start turning the other direction. So in here, I'm turning right. Over here, I'm turning left. Forever. And again, I'm going to say this again because I think it's nice. In this section here, where it's concave down, any tangent line I draw, any tangent line is above the function. Draw one yourself. Oh yeah, any tangent line I draw is above the function, as long as I'm not a terrible drawer. On the other side over here, where it's concave up, any tangent line is below the function. The reason I point this out is because what I really want to say is at the inflection point, the tangent line goes through the function. So if and I'm not going to draw it because it always looks bad when I draw it. But I'm sure this picture, in fact, there's probably a nice picture in this textbook right here. Maybe. I didn't look ahead, but I should have. Yeah, cool. Here's a picture right here of a point of inflection and the tangent line going through the function. So when you have an inflection point, the tangent line actually goes through the function, which I'm never good at drawing, so why even try? That's not a good ethos. Just because you're not good at something doesn't mean you shouldn't try it, but you know. I know my limitations for drawing things, so all right. Cool. Questions about this? So we're going to talk about second derivative for a minute, but are there questions about this example? All right, so let's talk about the second derivative for a moment and the concavity. But we kind of just settle the things really, but let's codify it a little bit. So if f double prime of x is greater than 0 on some interval, then we say that f of x is concave up on that interval. Similarly, and these are not the most important words I've ever written down because we're really going to draw some pictures that make it look much nicer. If the second derivative on some interval is negative, then we say that the function f of x is concave down. And this is really where it becomes important to understand the idea that a derivative, I mean, it's not the only, okay, there's lots of places where it's important to understand that the derivative is just talking about a rate of change. So when someone says the derivative of this function is positive, that means the function itself is getting bigger. Its change is positive. So if the derivative is negative, its rate of change is negative. The function is decreasing. So let's look at some very general pictures here, which I think your teacher has already drawn in class, but they're worth seeing again. So this function I've drawn here, this parabola-ish looking thing, is for sure concave up. So f of x here is concave up. Okay, big deal. Let's talk about what the derivative of this function is doing. And again, whenever you're, whenever you're talking about the behavior of a function, which direction are we thinking? Left to right or right to left? Always left to right. Always. We never really get a graph. Always left to right. I would say the one kind of exception maybe is if I'm talking about a vertical asymptote and I say both sides go up. Technically, one side's going up and the other side's going down, but like we say both sides go up because, okay. But that's kind of the assumption. So let's talk about the derivative here from left to right. So the very left, let me ask you all, is my derivative very negative or very positive? Is that slope of that line very negative or very positive? Very negative. You guys say whispering. I'm also kind of deaf and getting probably deaf. My wife would be like, yeah, okay. I'm not really, but like my hearing is not as good as it used to be. So I need you all to be louder. Okay, how about over here? More negative or less negative? Okay, how about here at the bottom? How about over here at the right? Okay, how about over here? Okay, so from left to right, did our derivative increase or decrease? Right, it got bigger. Very negative, a little bit bigger, less negative, a little bit bigger, 0, a little bit bigger, a little positive, a little bigger, more positive. So the derivative here isn't positive, right? The derivative itself is increasing. Okay. I want everybody to close their eyes. I want you to imagine a function that is increasing. It could be like a straight line. Okay. Is the derivative of that function positive or negative? All right, what do you all, you can open your eyes now. What do you all think? Is that derivative of that function positive or negative? The function's increasing, its derivative is positive. Okay, great. This function, f prime of x is increasing, its derivative, f double prime of x, is positive. All three of these things mean the same thing. If a function is concave up, the first derivative is increasing, the second derivative is positive. Also, now I can say my favorite part. Concave up, like a cup. And then on the flip side, literally we'll flip it over. Same idea, except now everything's reversed. So now f of x is concave down, like a frown. And the derivative is decreasing because it starts off on the left as very positive and then is less positive, 0, slightly positive, slightly negative, more negative. It's getting smaller, smaller, smaller from left to right. And then finally, the second derivative is negative. Because again, if something is decreasing, really, these are the words you should think. If something is decreasing, its derivative is negative. So if the first derivative is decreasing, the derivative of the derivative is negative. Cool. Yes. Yeah, we'll say that in a minute. Okay. So let's do some more examples. Unless there's questions. Okay. And let me see. Yeah, cool. Let's look. Yeah, that's a good example. Cool. So I will say I tend to be partial to examples that have asymptotes because I think they make us work a little harder. I don't know. Let's look at this example. Let's look at f of x equal to x squared plus 4 over x squared minus 4. Dun, dun, dun. Oh, yeah, that's going to be interesting. All right. And we're going to graph it. So we're going to graph this. Graph is a word full of meaning, right? There's a lot. Graph means do like 6 things at least. So thing 1, the y-intercept. So we're going to set x equal to 0. We're going to get y equal to f of 0, which is just 4 over negative 4, which is negative 1. X-intercepts. For rational functions, or for anything fractional, really, to find the x-intercepts, you're really just going to set the top equal to 0. So you could start by setting x squared plus 4 over x squared minus 4 equal to 0. But then your first step should be to multiply both sides by the denominator. If you do that, you're left with x squared plus 4 on the top, and 0 times anything is still 0 on the right. And then x squared plus 4 equal to 0 doesn't have any solutions, because x squared would have to equal negative 4, and that doesn't have any real solutions. So no solutions means no x-intercepts. Cool. Vertical asymptotes. Set the denominator equal to 0. In this class, actually, no. So when you get to 16b, you'll also see that the natural log or any logarithmic function also has a vertical asymptote. But aside from the logarithmic function, which we don't talk about in 16a, so no worries, the only way you get vertical asymptotes is by finding where you have division by 0. Specifically, not 0 divided by 0, but okay, fine. So set x squared minus 4 equal to 0. I would factor x minus 2 times x plus 2 equal to 0. And we're going to get x equal to 2 and x equal to negative 2. All right, let me ask you all, can you show me on your fingers what the horizontal asymptote is? Yeah. And I want to point out, it's not because it's 2 divided by 2. It's because those highest degrees are the same, and we have 1 divided by 1. That's why we're getting 1 as our horizontal asymptote. There are other ways, like this is the shortcut way of doing it, right? You could show more work. You can take the limit as x goes to infinity. And sometimes you do actually need to do that to be able to actually see what the horizontal asymptote is. But if it's a rational function like this shortcut is typically fair game to use. All right, we've done all the basic things. Now let's do the first derivative stuff. And here's where things get a little bit messy. Sometimes on exams, a teacher will give you a rational function like this and then also give you the first and second derivative because it's messy to work out and simplify. I'm not saying you should count on that. I'm just saying that's a possibility. I would probably it'll be obvious from your practice final whether or not that's going to be given to you or not. Or Tab will say something about it if you're in Tab's class. So let's see here. Okay, the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function, all divided by the bottom function squared. Yeah, okay, let's multiply it out. So I'm going to get 2x cubed minus 8x minus 2x cubed minus 8x all over x squared minus 4 squared. And then the 2x cubes cancel. The 8x's do not cancel. I get a minus 8x, which is minus 16x over x squared minus 4 squared. What's my critical value? What makes this equal to 0? Just 0. That was the answer. It was 0. There are two other numbers that are important here. If something is a vertical asymptote, it always ends up being something we should list in our critical values, even if it's not really a critical value. Is 2 a critical value? Maybe, kind of. It's what I call a pseudo critical value, because if you plug in 2, what do you get in the derivative here by plugging 2? I get undefined, which is something we look for, but to be a real critical value, it has to be in the domain of the original function, and 2 obviously is not. But we still want to include it in the sign chart. So we're definitely going to include both x equal to plus or minus 2. These are pseudo critical values. That's not a real name, or like that's not like an official name. It's just what I call it because I think it makes sense. So on our number line, I don't know if Tav has talked about that or not, but like it's most textbooks define these numbers to not be critical values because they have to be in the domain of the original function. Cool. So let's see here. So on our number line here, we have 0, 2, and -2. Pick a number bigger than 2, like 3. The top is negative. The bottom I shouldn't even think about, because if you're squaring the whole bottom, it's always going to be positive. So if I plug in something bigger than 3, it's going to be positive. Bigger than 3, bigger than 2, like 3, it's going to be positive. Between 0 and 2, can you fix my mistake? Can you not let me get away with that? I want you all should check x equal to 3 real quick. Is the derivative positive or negative? What do you think? Positive or negative? Positive, negative. I want some thumbs. Send me some thumbs. It's definitely negative over here. I wrote positive because I was saying words and trying to write the other words. I obviously can't say positive when I'm trying to write negative. It's definitely negative over here, right? Because we plug in a positive 3, we get a negative number on top divided by a positive number on the bottom. I plug in something like 1, still negative on top, still positive on the bottom. Even though 1 minus 4 is negative, a negative number squared is going to be positive. Negative there. If I plug in -1, now it's going to be a positive divided by a positive, which will be positive. If I plug in a -3, still positive on top, still positive on the bottom. So my function is increasing, increasing, decreasing, decreasing. Do I have a relative maximum anywhere? Yay or nay? Yeah. In fact, 0 is the only place I could have anything really, because we know that we have what kind of things at 2 and -2? vertical asymptotes. You can't have anything else. If you have a vertical asymptote somewhere, you're stuck. That's all you get. So we definitely have relative maximum at x equal to 0. Let's, yeah, sure. We can find, so here's the thing. When you have rational functions like this, usually finding the second derivative stuff is kind of gross. Let's do it anyway because it's good practice. So here's my first derivative. Negative 16x over x squared minus 4 squared. Our second derivative, all right, bottom times the derivative of the top minus the top times the derivative of the bottom. We have to be a little extra careful here. The derivative of x squared minus 4 squared, we've got some stuff squared. The derivative is 2 times our stuff to the first times the derivative of the inside stuff, which is 2x, all divided by our denominator squared, which is x squared minus 4 squared squared. So x squared minus 4 to the fourth. If you have something like, here's, cool, yeah. So here's what I know. Here's what you will know too. When you have a quotient like this and the denominator is already raised to a higher power, once you get to here, if you simplify this accurately, you should be able to end up writing it so that the new power in the denominator is 1 larger than the old power. Meaning I should be able to simplify this so it has an x squared minus 4 to the third in the denominator. And the reason that works is because I should be able to factor out an x squared minus 4 from the top. And I can actually factor out a lot of things from the top. So let's see what I can factor out here. I can factor out an x squared minus 4. I can factor out a negative 16. Let's see what we're left with here. So from this piece, I'm left with an x squared minus 4. From this piece, gosh, all right, there's lots of stuff here. I still have a minus. I factored out the negative 16. I'm left with an x. I'm left with a 2. I'm left with, I don't have any x squared minus 4 because I factored out the x squared minus 4. But I still have that 2x over there as well. Over x squared minus 4. The fourth. Does that look all right? That looks all right. Okay. Cancel. Why do I feel like I'm making a mistake? I don't know. Sometimes you just feel like you're making a mistake because you're like, yeah, okay. Anyway, let's finish this off. So I've got a negative 16. X times 2 times 2 times x is 4x squared. I have x squared minus 4x squared. That's going to be a negative 3x squared. And then I have a minus 4. Okay, yeah, that works out fine. Over x squared minus 4 cubed. All right, here's kind of, maybe not, no, it's a little disappointing. I'm not gonna lie, it's a little disappointing. If I set this equal to 0, well, again, when we set a fraction equal to 0, we really just set which part equal to 0? The top or the bottom? Top. If you're trying to figure out where it's undefined, it doesn't mean you set the bottom equal to 0. We already know where it's undefined. It's going to be undefined at 2 and negative 2. So we set this equal to 0, you're going to get the top, which is negative 16 times negative 3x squared minus 4 equal to 0, which is really negative 3x squared minus 4 equal to 0, which is really negative 4 equal to 3x squared. And right there is, I think, where we can see, no solution. X squared is positive. Multiply it by 3, it's still positive. It's never going to equal negative 4. If we're not, unless we're talking about imaginary numbers, which we're definitely not talking about imaginary numbers. So no solution. So you only get the x equal to plus or minus 2 as your pseudo critical values for the second derivative here. All right, let's plot them. I will mention this is good practice, but I will say usually you're going to feel kind of gross after this. Like, we kind of did all this work for what feels almost like nothing. Sometimes that's the way it goes. Let's throw those on there. We're looking at our second derivative. So pick a number bigger than 2. Oh, geez, pick a number bigger than 2. That looks terrible, but let's do it anyway. Like 3. Is this whole thing positive or negative? Yikes. I don't know. Negative. I plug in 3, 9 times -3, that's good. Oh, this is always negative, right? Right? X squared is positive times -3 is negative, -4 is still negative. Yeah, this is always negative. This is always negative. So really, we're just worried about the bottom part here. So plugging in x equal to 3, that's going to be positive on the bottom. So it's a positive. It's a lot of things to think about. Positive. And then it's going to change, and it's going to change. If I plug in 0, the top is definitely negative. Positive, the bottom is definitely negative. If I plug in something over here, positive, negative. So concave up, concave down, concave up. So where do we have an inflection point? Anyone have a brave answer? Let me ask a more generous question. Do I have an inflection point at x equal to 2? Maybe. Can I have an inflection point where I have a vertical asymptote? Definitely not. So to be able to have an inflection point, or to be able to have a relative max or a relative minimum, the function has to be defined at the point. And it's not, right? If you look back at the original function definitely is not defined at 2 and -2. So what I encourage, actually, which I think is a good idea when you draw these things here, is if you draw the number line here with your first derivative stuff, throw in your vertical asymptotes. Remind yourself that you can't have anything else there because there's a vertical asymptote there. And then same deal over here. I know it's going to be concave up over here, but then I have a vertical asymptote, and then concave down, and then a vertical asymptote. So I can't have inflection points there because the function is not defined there. All right, let's try to see what this thing looks like. So let's graph it. I know it feels like a lot of work to get to the place where you're finally actually graphing it. So we're going to go back and plug in all the things. So I got our y-intercept of -1, no x-intercepts, vertical asymptotes at positive and -2. A horizontal asymptote at y equal to +1. What time is it? Okay, I was worried for a second I was going too long. You guys would say something, right? And then that's kind of all the stuff we have to actually graph. Now we're just going to try and graph it. Now, if you are more comfortable, you're welcome to plot more points. I'm always trying to graph with the minimal amount of effort possible. So I'm looking back at my first derivative information because that's really the most helpful. I can see that left of -2. Sorry, you can't see that quite. So, come on, papers. To the left, I'm going to be increasing. So I know I have to be doing up like this. And then between -2 and 0, I'm still increasing. But now I'm concave down. So right, concave up here, concave down here. Change concavity. Now I'm concave up. And finally, did I blow it? I totally blew it. I wasn't paying attention. Does that match? So look, I should have been increasing, and then decreasing. Terrible. Try again. So it's good to look at your sign chart for your first derivative because sometimes, right? Okay. So let's try that one more time. I do like labeling the asymptotes. So, okay. Increasing. And then after this point, we're going to be decreasing. And then after that point, we're still decreasing. Well, if you're decreasing on the right side of the vertical asymptote, you have to start way up here. I will point out this function does have symmetry. Right? This is an even function. If you reflect it across the y-axis, it would look the same. Sometimes people like you to make note of that if you're graphing a thing. Maybe look at, oh yeah, yeah, cool, we'll do that. Questions before we look at, yeah, we can, yeah, cool. All right. No time for questions. Yeah, you know, it's a bad habit to ask for questions. You guys are welcome to ask questions whenever you have them, and you know that. I just always feel like I need to pause for like, anyone? Anyway, let's look at another example. Let's look at, yeah, let's look at that one. Sure. I feel like we might have done this one already, but it's still a good example. Let's look at x to the fourth minus 4x cubed. And we'll talk about the second derivative test and how its failures, in my opinion. So we're going to find all the things, we're going to graph it, but we're going to talk about how you can determine if a critical value is a max or a min based on something called the second derivative test versus the first derivative test. So we'll do both. So once again, we're going to graph this thing. So let's find all the usual things. It's not too terrible because it's a polynomial. So we know we can ignore the asymptotes. There aren't going to be any. So let's go ahead and find the y-intercept. F of 0 is 0. X-intercepts. Set this whole thing equal to 0. We should factor it. Factor out an x cubed. So you're going to get x equal to 0. X equal to 4. Cool. First derivative stuff. I feel like there's not a better way. Like first, when I say like we're finding where it's increasing, where it's decreasing, relative maxima, relative minima, it's easiest just to say that's all the first derivative stuff. Increasing, decreasing, maxes, mins. So let's find our critical values. So we're going to take our derivative, 4x cubed minus 12x squared, set it equal to 0. Factor out a 4x squared, left with an x minus 3. So we're either going to get x equal to 0 as a critical point or x equal to 3 as a critical point. And let's talk about how you can see if these are, well, in fact, I'm going to skip the sign chart for a second. We're going to come back to it, but I want to talk about how you can tell these are maxes or mins based on the second derivative test. So let's go ahead and find the second derivative. So my second derivative is going to be, I don't like the factored form for finding my second derivative. I would much rather use this version of my first derivative to take the derivative of, not this factored version, because I don't want to use the product rule if I don't have to. So taking the derivative of this, I'm going to get 12x squared minus 24x, which I do want to factor. Yes, we're going to find the critical points later. For now, I'm just factoring out a 12x, and I'm left with an x minus 2. Okay, here's what the second derivative test says. Second derivative test. If I'm going to say words first, we'll write that something in a second. If you have a critical value from the first derivative, then you can tell it's going to be a maximum if you plug it into the second derivative and it's negative. Here's why. If you plug in a point to the second derivative and it's negative, it means it's concave down. And if it's concave down at a relative maximum, sorry, if it's concave down at a critical point, then it had to be a maximum because the horizontal tangent is a horizontal tangent, meaning it's opening downwards and you have a tangent line. Otherwise, and then, so sorry, I feel like I'm not saying all the words exactly right here. So basically the idea here is, let's just look at it. If we look at f double prime of 3, for example, f double prime of 3 is 36 times 3 minus 2, which is positive. That means that the function f of x is concave up at x equal to 3. But we also know that x equal to 3, the tangent line is horizontal. F prime of 3 is equal to 0. So we have at 3 is something that has to look like this. There's no other choice. You have to have a horizontal tangent. It has to be concave up. So actually, I'm gonna wait a minute to write down what the actual second derivative test is. On the other hand, and this is where the second derivative test kind of fails. If you plug in your critical point from the first derivative, the other one was 0, and if I plug in 0, I'm going to get 0. This is inconclusive. You could still have a maximum or a minimum. You could have a inflection point. So this is why I don't love what's called the second derivative test for testing maxima or minima, because if it's equal to 0, it's inconclusive. Whereas with the first derivative test is always conclusive. It's always going to tell you if you have a maximum or a minimum or neither. Right here, if I pick something bigger than 3, positive, between 0 and 3, negative, less than 0, also negative. So my function is decreasing, decreasing, increasing. So look, I definitely have, as we knew we would, a relative minimum at x equal to 3. And at 0, we don't have a relative extreme. We probably have an inflection. Usually, if you don't have, oh my God. If you have a critical point, that's a critical point for the first derivative and for the second derivative. If it's not a relative extrema, it's an inflection point, or vice versa. If it's not an inflection point, it's usually a relative extrema. So looking here, if we look at the second derivative sign chart, which I should be putting not just 0 on, what other number should go on my second derivative sign chart? What other nice integer number by setting the second derivative equal to 0 should I get? Show me on your fingers. What is the other number I'm looking for? It only requires one hand. So if I set the second derivative equal to 0, I get x equal to 0. What else do I get? Yeah, it's equal to 2. And then if I look at the sign chart for the second derivative, I pick something bigger than 2, like 3. 3 minus 2 is positive. 12 times 3 is positive. Positive over here. Between 0 and 2. Or really, I could do the thing where I look at the powers. The powers are both odd, so we're going to change and change. Or you can plug in 1 and get positive times a negative. You plug in -1, negative, negative. So our function is concave up, concave down, concave up. How many inflection points do I have? 0, 1, or 2? I think I have 2. I have an inflection point at 0. I have an inflection point at 2. Since I'm going to graph this thing, I really should also find the y values. So the y value is going to be f of 0, which we already found to be 0. And here the y value is f of 2, which is 16 minus 4 times 8. This is an example of where I should have factored it. I should have said this is x cubed times x minus 4. And then plugging in 2 is a little easier. 2 cubed is 8, 2 minus 4 is -2, and 8 times -2 is -16. How much time have we got? Oh, we got enough time. Okay, cool. All right, let's look at the graph. So let's make a giant graph. Some points here. 4. I'm usually I like to make my x-axis pretty well defined. The y-axis, I don't usually mark anything until I draw the graph, if even then. So I know I have an x-intercept of 4 and it's 0. My y-intercept is also 0, obviously. My relative minimum is x equals 3, and I did not find the y value. I guess you should go back and find the y value. So f of x is x cubed times x minus 4. F of 3 is 27 times -1. It's -27. I'm not going to try and go to scale there, right? -27 is probably off the chart with the scale I've made. I'm just thinking I know it's going to be something down there. So my function is decreasing, decreasing, increasing. And then I know I should be concave up, concave down, concave up. So concave up means, when I think of concave up, I think of an upward opening parabola. That's like the easiest thing for me to think of. So when I draw it over here, even though it's not technically a parabola, I'm going to draw it kind of like it is. I'm going to draw it like this, trying to smooth out at the bottom there. Now, concave down means it's going to look more like a downward opening parabola. So it's going to be more like that. And then when I get to ooh, when I get to 2, right, at the point 2 comma negative 16, that's where my concavity switches. I say, okay, instead of going this way now, I have to kind of switch and be going the other way. Bottom out, and then, oh, missed your point. That's why you don't mark your points ahead of time. That's why it's good to like not draw these little marks here. So then there's my inflection point approximately at 2 comma negative 16. There's my relative and global minimum at 3 comma negative 27. And there's another inflection point at 0, 0. Something to say here? I don't know. A couple things to say here. Oh, I know what I want to say. So again, just as a reminder, I think it's really nice to see that where it's concave up, all your tangent lines are below. Where it's concave down, all your tangent lines are above. Concave up, below. And if your inflection points, the tangent line goes through the graph. Which, there you go. Look, I even drew it, kind of. Let's talk. Yeah, we got 5 minutes left. Let's talk for a little bit more, just more about what the second derivative test actually says. So here's what the second derivative test actually says. Second derivative test for relative extrema. The reason we really talk about this is because when you take 16C, this test comes back. And we actually have to use it because there isn't a, so in 16C, you graph functions of 2 variables. Like instead of like y as a function of x, you graph z as a function of x and y. So it's kind of like it's like a blanket, kind of, is what I really think of. It's like a blanket that's been like kind of out in space, and you're trying to find out where you have a relative maximum. And you can't do the thing where it's increasing, decreasing, because you don't know which direction it's increasing, decreasing from. So instead, you have to use the idea of the second derivative test, which is that if the function is concave down, you have a relative max. The function is concave up, you have a relative minimum. So that's kind of the basic idea. So I never know how to write this very well. So for a critical value C of your function f of x, or critical value, sorry, I forgot a word there, of f of x, meaning that f prime of C is either 0 or undefined. Right, you can totally have a critical value where the derivative is undefined. Sorry, I'm trying to think of the right words to say here. We have that C comma f of C is a relative maximum if f double prime of C is, all right, to be a maximum, we need to be concave which way? So f double prime of C had better be positive or negative? Negative. So if you have a critical point from the first derivative, it's a relative maximum if f double prime of C is negative. Similarly, we have that same point, C comma f of C, is a relative minimum if the second derivative at that C is positive. And unfortunately, if f double prime of C is equal to 0, you don't know anything. It could be a max, it could be a min, it could be an inflection point. This might be an old reference, but if f double prime of C is equal to 0, you're Jon Snow. You know nothing. Too old reference. No, you guys didn't watch Game of Thrones? Okay, well, it was a thing people said for a while. You know nothing. You're Jon Snow. Okay, we know nothing. Here's some examples of what I mean. So 2 examples to take this to heart. F of x equal to, let's make it a little bit more fun. F of x equal to x minus 1 to the third. You know what this looks like, or you just have a decent idea of what it looks like. X to the third, usual cubic graph. I'm shifting this 1 to the right. So this looks like, I always pick this graph and I'm like, oh, I'm not good at drawing this graph. Oh my God, terrible, James. So this graph has an inflection point at 1. F prime of X, is equal to 3 times X minus 1 squared. Set that equal to 0, you get X equal to 1. F double prime of X is equal to 6 times X minus 1 to the first. If you plug in 1, F double prime of 1 is equal to 0. But if your function was, say, X minus 1 to the fourth, X equal to 1 is still going to be a critical point. Your derivative is 4 times X minus 1 to the third. Set that equal to 0, you get X equal to 1. That's a critical value. But then if you take the second derivative here, that's going to be 12 times X minus 1 to the second. And if you plug in 1, F double prime of 1 is also 0. But for this graph, X minus 1 to the fourth looks like this. So it's a little steeper than that, but you know. So here's the point, and I really want to make this super duper extra clear. The second derivative test sucks, is really my point. That's really my point. The second derivative test is terrible. You shouldn't use it unless you were asked to or you have to. That's not entirely true. There are sometimes when it's really kind of like, I will say it's better for optimization problems some of the time, which we're going to talk about soon. For optimization problems, sometimes it's easier to take the second derivative and be like, is my critical point giving me a max or a min? But for graphing, since you're already going to make the sign chart for the first derivative already, it's really easier to see if you have a relative maximum or relative minimum based on the first derivative test. But the second derivative test is all this. But if you get your second derivative being 0, maybe you had an inflection point. Maybe you had a minimum. You cannot tell from the second derivative test if it's equal to 0. So that's why then you have to go back to the first derivative test. So just want to point that out. If you're using the second derivative test and your second derivative is equal to 0, you have to do something else. These examples show it, right? Your second derivative could be 0 and you could have an inflection point. Your second derivative could be 0 and you could have a relative minimum or maximum.